Hi, welcome to Computational Chemistry with Ali Sudais. Today we're going to talk about the Newton-Raphson Method, and this is lecture number 3. My name is Ali Sudais. I'm Computational Chemist, MD of ACA, Ali Coaching Academy, Motivational Speaker, and ITA Instructor. What Newton-Raphson Method is? So Newton-Raphson Method is actually the basis for, This is the basis for geometry optimization procedure. Basis for geometry optimization procedures used in most computational chemistry codes. Do you know about the Hooke's law? First, we should know that there is a law. Its name is the Hooke's law, and you know about the Hooke's law, which is F is equal to K minus K x square. Okay, like in the last lecture, we also talked about this. If you want to know about the computational chemistry, you must know about the Hooke's law. So you can see in here that EI minus delta E naught, so we call it delta E, is equal to Ki minus Q naught, and this is whole square. So this is K and consider it as x square. For 1D harmonic potential, harmonic is where the both sides are equal, like this one and this one. This is called harmonic. You can see we took a gas structure and its energy is this one. Okay, its coordinate is Qi and energy is Ei. Okay, and it becomes optimized in the very first step. So it jumps directly towards the minima and it optimizes. So this is Q naught and E naught, and the bond length, this is the bond length. It means that only there is the need to change the bond length in here, and it comes directly and it jumps to big optimize. Okay, and you can see this is the energy. The energy lowers, comes down, and it optimizes, and the bond length changes only. So this is how this works. Newton-Raphson method tells you about the K minus K square, so we can write it in here, Ei minus E naught. Ei, you know now that Ei is actually the energy of the initial one, and the E naught is the energy of final one. Okay, now you can see if we take the first derivative of this one, it will become delta E divided by delta Qi. Okay, and this will become, this 2 will come here and it will become 2K Qi minus Q naught, and the power will decrease by 1. Okay, it will become 2 minus 1, so this will become 1, and that will come here, and this 2 will come as a coefficient in here. Okay, so this will become delta E divided by delta Q and I is equal to 2K Qi minus Q naught. Is it clear? Okay, then we take the second derivative, and when you take the second derivative of this one, when you take the second derivative, this will become delta square E divided by delta Q square I is equal to 2K, and this will become Qi minus Q1. And the same rule applies again in here. 2, if the power will decrease to 1 and the power will decrease to 0, and when the power is 0, it will become is equal to 1. So that the second derivative is equal to, which is delta square E divided by delta Q square is equal to 2K. Clear? Now what you do, there is a very simple way. Now you know about the first and second derivative, that the first derivative is equal to delta E divided by delta Q is equal to okay, you know that in here, this is the first derivative which is important. Delta E divided by delta Q is equal to 2K Qi minus Q naught. Now what you do, the 2K has this value, right, and add this value in here. this will become like the 2k. The 2k has value this one, so you just remove this 2k and add this value, and so these two equations will give this equation, which is delta E divided by delta Q. The first derivative is equal to second derivative delta square E divided by delta Q square into Qi minus Q naught. So we have a final equation, and you can just take this Qi from here. This Qi will go to the other side, and it will become Qi is equal to Q naught minus, this will come by itself, and what you do, you divide both sides with the delta square E divided by delta square Q. When you do it, you will get this one. Clear? I hope this is not difficult. You can just do it by yourself, that when you want to take Q naught only, in that case, what happens? This happens. Okay, so you can see in here that in the 1D Newton-Raphson, which is the basis for geometry optimization procedures, uses most computational codes. So it tells you about this one. Now let's move towards the next slide. The next slide tells about the Newton-Raphson, and if this is not an harmonic, like first what we talked was harmonic completely. If the system is not harmonic, so what will be the PES? What will be the potential energy surface? So we cannot find Q naught in one step. First we had just one, so we could find in one step, okay, but now we cannot find in one step, because there will be iterations. Iteration mean first it will do calculation, will give this one, then it will do again calculation, will give this one, and then it will do calculation and give this structure, and finally it will give you a minimum, this one. It means that this is not one, this from here to here, this is not one calculation, but this is actually a combination of calculations. Okay, so we studied in the last slide that for 1D, this is for 1D. So you know that the equation for 1D is Q naught is equal to Qi into first derivative divided by the second derivative. Okay, so this is very clear from here. Now you want to know about the more than 1D. So what you do, you can just take it as the derivative for the first step. Let me just take it. Okay, okay, this one. This is for first step, or for one step we take this one. So consider this is the first step, this one. Now you want to, so therefore we add the I plus 1. So there is the 1, you can see this is the I and I. Now you want to write the equation for this one, for the second one. What will you do? You will write plus 2. This is plus 1. You will write plus 2 in here, and the rest of all is the same. You see Qi will become plus 1, will become plus 1, plus 1. You should remember, if there is plus 1, there will be nothing. You see, if there is 2, there will be 1. If there is 3, there will be 2. There will be 4, there will be 3, and that's Qn, so n minus 1. This is the final equation. You should know that it will give. Now you can see that this is the first step and this is the second step. This is the second step, and then the third, fourth, fifth, sixth, and this is the nth step. Nth step. So you know now that the equation is Qi is equal to Q naught minus first derivative divided by the second derivative. You should remember this one. And then for a system which is not harmonic, then if this is not harmonic, then you will get different equations, and the equation you can get is Qn is equal to the last one. You can see Qn is equal to Qn minus 1 minus, you should remember this minus sign, that minus, this minus sign in first derivative divided by n minus 1 divided by second derivative n minus 1. It means there is only n in here, and the rest of all they contain n minus 1. If you remember this one, this will become easy for you. So you can see in here that on one side, there is a reaction coordinate q, and in here there is energy. But when we take the for 1D, you can see for 1D the energy is here, but in here we have just one coordinate, and that is bond length. For more than one, where this is not when the sorry, when the system is not harmonic, then you do not take just one, you just write the coordinate q, sorry, not q, yes, q, this one, you write just the q, this one, the reaction coordinate, and in here you write the bond length. Okay, now instead of we iterate until force on nuclei derivative gradients are small. What does it mean? It means that the calculations are going on and until the minimum is obtained. With a reasonable guess structure, you just take the first, this is the guess structure, the first one. Most programs will find the nearest local minimum. I mean, it will go to the nearest local minimum where it can give you the minimum energy. It takes mostly 10 to 20 iterations. Okay, it will get 10 to 20 iterations. I mean, 10 to 20 calculations will be will follow, and then it will give you the minimum. Transition states can be more difficult to locate, and the transition states, for example, it gives you a saddle point on a high energy, so this is difficult to locate at this point. So therefore we say that the transition states can be more difficult to locate. Note, and this is very important note, it doesn't just follow reaction coordinate but optimizes over whole PES. Okay, that it doesn't follow reaction coordinates but optimizes over whole PES. Okay, now we are coming towards the next Newton-Raphson. You know about the, if there is for one calculation you write this one qi plus 1 so qi minus first derivative divided by the second derivative, and which is equal to qi, this one, qi plus 1, qi again in its own place, and then the first derivative, this derivative is called g. We're going to explain this further, and this one is called I, Hessian, H. It means this equation will give you another equation, which is qi plus 1 is equal to q naught minus first derivative divided by the second derivative. We write like this. For the first derivative you write like g, and the second derivative you write like h. It will become g h minus 1 or h minus 1 g, like this one. Okay, now you can see in here they will give you this one. Now you can see that we have a column matrix in here. There are column matrix in here. If you have qi, q is equal to I, qi, 2i, 3i, 4i, and 3 in I. Okay, the first derivative, this is the first derivative, which is equal to gi. It will give you the first derivative, this one. The second derivative, you see there's q1, q2, qn, 3n. Okay, now the second derivative, which is equal to this one, it will give you the second derivative, q1, q1, q2, q1, q3n, q1. You can see this is 3n and 3n, these are same. When you move towards this one will become this, in here this one become 2, and in here this one will become 2, and then go to 3n. Okay, so if you come diagonally like this, you will find that this is q1, q1, q2, q2, and q3n, q3n. Okay, this is how you have to follow. Sorry. Okay, so this is how you have to follow you can know about the Newton-Raphson for more than 1D. So optimization is done using 3n Cartesian coordinates for 3n, Actually this is for the 3n Cartesian coordinates. So you can see first you should take this one and then this one. It will give you the Hessian. When you combine it will give you this equation. Okay, so this is very clear now that Newton-Raphson is very easy, not a difficult one. Now we have the QI. We explained this already, but in here we can just talk in a little detail about all these. Okay. First is QI, which is column vector of 3n. We said this column vector like this. Column vector of 3n Cartesian defining the molecular geometry. What does it tell you about the molecular geometry? How the geometry is. Initial gas structure should look like anticipated minimum or transition state. Like for example, you want to get an anticipated minimum, then you should take a gas structure which is exactly like that. Like you just try to construct a structure which is exactly like the real one. For example, you constructed this one and it gives you another one like a structure, but it should be the same like this one. You shouldn't say that it should. You shouldn't construct a structure which is difficult or different. If it is different, then it will not give you the real structure. Okay, so what does it say? It says that sorry, it says that the QI is the 3n column vector of 3n Cartesian coordinate and defining molecular geometry. This one. What is GI? This is the 3n derivative for energy with respect to Cartesian coordinate. So this is also a column vector. This is also a column vector. QI is also a column vector. This is also a column vector. This is 3n Cartesian coordinate. This is 3n derivatives of energy. Okay, you should know the difference. This is 3n Cartesian coordinate. This is 3n derivative of the energy with respect to Cartesian coordinates. Now it represents the force on the nuclei, which is equal to if A is equal to minus delta E divided by delta QA. If you remember the first derivative, then you should remember this one as well. This is the forces on the nuclei. The nuclei forces, I'm sorry. Okay. Then there's an calculated by the program that is almost 20% of the effort in geometry optimization. Okay, so GI, it has almost 20% of the effort in geometry optimization. Now we come towards the HI, which is Hessian. HI is the Hessian. The Hessian, you can see Hessian is the matrix containing 3n into 3n. Second derivatives of the energy with respect to Cartesian coordinate. So this is that was the first derivative, and in here it is the second derivative. This is, you can see, this is the 3n derivatives, and in here this is 3n into 3n second derivatives. HI is 3n into 3n second derivative of the energy with respect to Cartesian coordinate. Second derivatives are expensive to calculate. These are expensive. Generally estimated during the optimization is the second derivative. You know that delta square E divided by delta Q A and B, which is almost equal to the difference in delta E by delta B divided by delta Q. Okay, I. This is how you can, if you go back, you can see in here. This is HI, the 3n 3n. You can see in here. This is the 3n 3n. Finally, this one, the 3n 3n. And the other one, this one, and in here is delta E divided by delta Q 3n only. Okay, so now you know about all these things, that the Newton-Raphson for 1D and 3D. This is the 3D. Okay, now the finding minima, like the minimum. How can you know? Now you know about what is now you know that what is H and G, and which is Hessian and G. Now construct a gas structure. First you should, if you want to find a minima, you should construct a structure. For example, you constructed this structure, we call it a gas structure. Optimize will go to the nearest minima. You just took it, and for example it is like this, it will give to the nearest minimum. Okay, although it is not harmonic, and it will be like this, first here, and then it will go like this. So this is not harmonic, this is enharmonic. Build up initial Hessian. So we talked about the initial Hessian HI and approximate from low energy, low level calculation and calculate derivative, then GI. First the initial Hessian HI, then GI, which is the initial GI. Compare derivatives against convergence criteria, and then you should compare it. Convergence criteria is convergent sorry, convergent criteria meets or not. Update geometry, so qi plus 1, qi minus hi, gi, h is minus 1, which is actually gi divided by hi. Okay, update Hessian, you should update the Hessian, which is the first derivative divided by, sorry, first derivative is the second derivative, this one, delta square e divided by delta q a q b I, which is delta is outside now, delta e divided by delta q b by q delta q a. Repeat 3 through 6 until convergence criteria are met. Until the criteria are not met, the system will do again and again the calculations, and you have to do all the calculations again. That if you, when the convergence criteria are met, it means that is your structure. Now, what is the convergence criteria? So, actually, this is impossible to find the exact location. Like, if this is a structure, this is the harmonic, for example, this is a system where it comes to the minimum in here, for example, it comes in here. So this in here, this is very difficult to get the exact minimum. Now you don't know this is the minimum, this is, or this is, but therefore this is impossible to find the exact location of minimum. This is impossible to find the exact location of minimum. Instead, geometry optimization stops when all derivatives are small. Like when all the derivatives we talk about further, the all derivatives are small, the geometry optimization stops. It means that is your optimized geometry. Okay, so in most codes, maximum force is less than 4.5 into 10 raised to the power minus 4 Henry per Bohr. You should remember this unit. Okay, this is the unit of, we have 4 actually, maximum force 2 and RMS 2 forces and 2 RMS. Now this is the maximum force 4.5 into 10 to the power minus 4 Henry per Bohr, and RMS is actually 3 is less than, sorry, less than, okay, 3.0 into 10 to the power minus 4. So both are 10 to the power minus 4, and here this is 4.5 and in here this is 3. You should remember this one. Other geometry based criteria, but these are the main that that for convergence you need to know about the yeses of these in the, okay, yeses, you need yeses, 4 yeses. If you know about the 4, if you get the 4 yeses, it means your structure is optimized. Now what is the difference between these two? If you see this one and in this one, in here you can find that this is approximate from low energy, low level calculation. So you have to build up the initial Hessian HI for the finding minimum in here. But what if you want to get the finding transitions, right? So you will find that these in this slide, these are almost same. Okay, in here you can see the same. What is the difference? I'm going to tell you the difference. You see, same construct a guess structure, but it needs a very good guess structure for transition states. Build up initial Hessian HI, calculate analytically. This is the difference. Like the Hessian should be calculated analytically. Okay, then calculate GI, compare derivative against convergence criteria, the same, and update geometry. QI plus 1 is equal to QI minus HI minus 1 GI. Modify H for TS. Okay, you have to modify this. Update the same Hessian, delta square E divided by delta QA QB is equal to delta E divided by delta QB divided by delta QA. Repeat 3 through 6 until the same process we talked about. Okay, initial structure, so initial guess. Finding a settled point is difficult, need a good guess structure, accurate Hessian. Like in here, this is very difficult to guess the structure. The settle point, find the settle point is very difficult. Like if it is like this is the settle point. This is very, very difficult to find. Okay, so therefore the settle point is difficult. Need good structure, you need to draw a good structure and accurate Hessian. Guess structure by preliminary scan along with the reaction coordinate. You should remember this, that there should be a preliminary scan along reaction coordinates. Interpolate between reactants and product structures and chemical intuition. These are the three ones. The first one is you should know about the the preliminary scan along with reaction coordinates, interpolate between reactants and product structure, and chemical intuition. So initial guess, the guess structure by these three processes, and you should remember these three, all of the three. Okay, now let's move to the next slide. Okay, characterizing stationary point. Now we talk about the stationary point, that how can we characterize the stationary point. Convergence criteria are based only on derivatives. For stationary points, convergence criteria are based on only derivatives, like we talked about delta E divided by delta Q, like that. Definitions of minima and transition state involve second derivative. Now, minima and transition states, these two involve second derivative. How? The minimum. For example, you have like this, delta E square divided by delta Q is more than 0 for all Qi. It means this is Qi, this is Qi, and you want to get in here delta E will be 0, delta E will be 0, this will be, the first derivative will be 0 for all, but the second derivative, that is delta E square, this is the second derivative, delta E square divided by delta Qi is more than 0 because it will go up. You see, this will go up. So therefore, this is more than 0. For transition state, this is the transition state, and this will come downward in here to this side or this side. Therefore, this is the delta square E or delta divided by delta Q square I is less than 1 for exactly 1 Qi. 1 Qi mean the transition state. For 1, this will be in negative. Okay, like less than 0 definitely is in negative. It means for all others, for all other Qi, delta square E divided by delta Qi square will be more than 0. So need second derivatives to characterize minima or transition state. Characterizing stationary point, you should remember that the transition state involves second derivative. Second derivative tells you about the difference of the reactants, products, and transition states. And for the transition state, the second derivative will be negative, while for the reactants and products, the second derivative will be positive, or more than 1, you can say, more than 0. The last point, that frequency calculation and normal mode analysis. Right. Frequency calculation and normal mode analysis can be done with these processes. Normal mode calculation. What is normal mode calculation? Normal modes are modes are collective vibrational motion, like you can see here, collective vibrational motions of atoms, simplest vibrational motions in a molecule, probed in IR Raman experiment, and 3N minus S moles molecule per molecule, or 3n minus 1, 3n minus 5 if linear. Okay, it means if you have H2O, 3n minus 6 is for here. There are 3 atoms, 3 into 3 minus 6 will give you 9, minus 6 will give you 3. So there are three freedom. Yes, wait, let me explain it. Let me explain all these. If we just, you can see in water is doing bending, symmetric and asymmetric stretch, like it does 3 of these. So frequencies in harmonic approximation, you can see in here, this is harmonic, okay, but you can see in real this is not harmonic, this one. You can see the difference between these two. Collective vibrational motions. Number first, collective vibrational motions, simplest vibrational motions, probably in IR Raman, 3n minus 6 moles per molecule, and for non-linear, for linear, this will be 3n minus 5 if linear. Frequencies in harmonic approximations. What the frequencies are? Okay. The frequencies in harmonic approximation, let's talk about the frequencies in harmonic approximation. PS is approximately harmonic at stationary point. You can see in here, this is almost harmonic at stationary point, which is equal to, for harmonic we write 1 divided by 2 pi c k by mu, which is under root this one. Okay, k is the force constant divided by mu, and its unit is per centimeter. K is force constant, which is equal to delta square E by delta Q, which is the second derivative. You can see this is the second derivative we saw before. Mu is reduced mass of the mode. So 1 by 2 pi c into K by mu under root, or half, 1/2. C is for speed of light. So this is for speed of light, you can see in here. So if you do normal mode calculations, it tells you about, it can give you information about collective vibrations, simplest vibrational motions in a molecule, ion Raman experiments, 3n minus 6 mode molecule. Okay. You can see in here for water there is bending, symmetric stretch and asymmetric stretch in here, and frequencies can be when they are harmonic at stationary points, this will be 1 by 2 pi c into k by mu half. Okay, now normal mode calculation. Normal modes are eigenvectors of the Hessian H, and force constants are the eigenvalues. Okay. Normal modes are eigenvectors of Hessian, and this is the H is the force constant, or the eigenvalues. Diagonalization. We talked about the diagonalization before, but a little bit in here you should know. Square matrix A can be broken down into the products of 3 square matrices. Sorry, A. This is a square matrix. It can be broken down into P, D, P minus 1. Do you remember we just talked before that G, H minus 1 Hessian? The Hessian was in minus, like it was down. So therefore we just say that the normal modes are eigenvectors for Hessian, and force constants are the eigenvalues. So P is the square matrix column or eigenvectors. Well, let's see here. You can it will be understood easily. Okay, P is the square matrix in here, and columns are eigenvectors. The columns are eigenvectors. D is diagonal matrix. What does it mean, diagonal matrix? If you see diagonally in here, this is Qi 1 Q2 2, this will be Q3 3, and if you just come like this diagonally, you will find that this gives you a diagonal matrix. The diagonal elements are eigenvalues. These are what? These are the eigenvalues. You can see in here Q11, Q22, 3n, 3n, this one. In here you can see K1, K2, K3, K3n, etc. These are diagonal. So when they are diagonal, they will give you these one. Okay. Now this whole is Hessian H, this whole is P, this is K. So it gives you H is equal to P K P minus 1. This is P, okay, this is K and P minus 1. So this gives you this final equation A is equal to PD P minus 1 or H is equal to PK P minus 1. Okay. I'm sorry. Now we have the normal mode for normal mode calculations. We know about the H is equal to PK P minus 1. What does it mean? It means that you can see this diagonal relation in here, which is Q11, Q1, 2, 2, 3, and 3n. Okay, and in here you can see 2, 3 like this one, and this is 1, 2, 1, 3, 1, 4, 1, 5, etc. like this. Columns are nuclear displacements associated with the normal mode. The columns, these columns are nuclear displacements associated with the normal mode. First index designates direction. First index designates direction. Second indicate modes. Mode is 1 minus 6 are translation. I mean, we know that there are modes. So from 1 to 6, there are translation and rotation. So 1 to 3, there will be translation, and 4 to 6, those will be rotation. And onward, 7 to 3n, they all are vibration. If you want to know about the degree of freedom, then definitely you need to know about the 3n minus 6, and you should remember remove the translational and the rotation, then you can get the rest of the vibrational modes. Okay, now see, diagonal elements are force constants. These diagonal are force constants. It means this will be second derivative. K1 to K6 corresponds to translation and rotation, as we talked in here, 1 to 6. So K1 to 6, K6 in here, this will be translation first and then rotations, and more than K6 like K7 to K3n are vibrations. The rest of all are vibrations. Mass weighting gives the vibrational frequencies. We saw this before when we were talking that it is harmonic at minimum. So 1 by 2 pi c into k by mu and under root or half, whatever that is the same. Okay. P and K are useful for. Why P and K? They are useful for characterizing stationary point. Okay, in normal mode calculation, you can know about the stationary points for P and K. Visualizing normal modes. Visualizing mean you want to see the structure. Calculating 0-point vibrational energies. Okay, if you want to, we will study this further in the next slides. Simulating IR Raman spectra, a future lecture, of course. Finite temperature corrections, a future lecture. Okay. So these are the 5 points you should know for the usefulness of P and K. That if you want to know about the stationary points, if you want to visualize, you can get the 0-point vibrational energy, IR Raman spectra, finite temperature correction. These are the future lectures. Okay. Characterizing stationary points. Minimum. So you know about the minimum, which is the second derivative delta square E divided by delta Q. I square is more than 0 for reactants and products. All positive elements in H all diagonal elements of K are positive, right? If K is positive, the frequency is positive. Like if the K is positive, the second derivative is positive, which is equal to K, it means this whole will be positive. So mu bar, whatever that is equal to 1 by 2 pi c K by mu. This will also be positive. Minimum are categorized as having all positive frequencies, minima. Transition state. So we talked about that. For the transition state, this will be less than 0, like negative, for exactly 1, okay? You should remember this one. One negative element in H Hessian, one diagonal element of K is negative. It means one of the diagonal element will be negative, which is of the stationary point, okay? The transition state. The if in here we say we saw that if the K is positive, the whole frequency will be positive. In here, if K is negative, the whole frequency, so that is called imaginary frequency, that will be negative. So transition states are characterized as having exactly one imaginary frequency. If there is one imaginary frequency, so that will be transition state, and if there is more than one imaginary frequencies, more than one will give you the hell top. Okay. Now, characterizing the stationary point, yet get the right number of frequencies, but does the structure make sense? Okay, like you got the exactly same right number of frequencies, but do you know that the structure makes sense? So what you have to do, what you're gonna do, you see the minimum, look the structure, and you can usually tell. Transition state. For transition state, there are a lot of saddle points on PES, not one. The transition state for your reaction should be the saddle point to connect the reactants and products. For example, there are too many. Sorry. Again. There are, for example, too many in here. 1, 2, 3, etc. Now, which one is your saddle point? The one which connects exactly the reactants and the products. That will be your stationary point. That is how you can know about the stationary point. Is it clear now? I hope. I'm trying to make it easy. Example of K2 enol tautomerism. You know about this one? From where this proton moves, this is connect TSV, and this. There are two energies. One is 244, not energy, V. There's one is 2449 and the other frequency is 2185.6 I per centimeter. There are these two. So how can you know that which one is the correct one? So the one with high frequency, that will be the correct one, and with the lower, this will be the incorrect one. Okay, characterizing the transition state. If you want to characterize the transition state, you should look at the structure. Is the structure okay or not? Does it look right? Pretty weak confirmation method, but helpful sometimes. Like you can't know exactly, but this is very helpful. You can't say that this transition state is exactly from the structure. The energy of the transition state must be higher than reactants and products. The second one is the energy must be higher than the reactants and the products. Okay, this is the second point you should know. The third and very important, which can help most of the chemists in finding out the transition state, is animate the normal mode with imaginary frequency. There will always be a transition state, one imaginary frequency. So you should see that imaginary frequency, animate the normal mode with that imaginary frequency. The normal mode with the imaginary frequency corresponds to the motion of the molecule over the energy barrier. Does the motion connect the reactants and products? Like you should animate, it will move like this and like this, like to and fro in here. And you should know that it comes from here to here or here to here. It means that if you animate in the normal mode with the imaginary frequency, it gives you the motion of the molecule over this energy barrier, and energy barrier, and it connects these two. The motion connects these reactants and products. If they connect these reactants and products, it means that those are it means that this is the transition state. That is how you can characterize the transition state. Okay. Perform the fourth one is the intrinsic reaction coordinate, IRC calculation. And IRC calculation start the transition state and follow the lowest energy pathway in each direction along the imaginary normal mode. Do these pathway lead to the reactants and products? Okay, IRC calculation, what does it do? It starts the transition state and follow the lowest energy pathway, like in here, this one. IRC calculations are expensive and rarely necessary, but they are a surefire way to characterize the transition state. IRC can exactly tell you about the structure, that yes, this is the transition state, or this is the structure of the transition state. Okay. So there are the 4 points. These are the main 4 points. First, you should look at the structure. Does it look like? This is a very pretty weaker. Second is the energy of transition. The energy must be higher than reactants and the products. And the third is animate. And the 4 is you should do the IRC calculations. These are the 4 to characterize the transition state. Okay. Now, relative energies. Once you identify the reactant, product, and transition state, like we characterized it before. If you know about the reactants, products, and the transition state, energies could be calculated relative to reactant. For example, this is reactant. It has this energy. You can see kilocalorie per mole. This is transition state. This is the product. For the reaction, if you want to know about the energy of the reaction, you should E of the product minus E of the reactant. It will give you the E reaction, energy of the reaction. If you want to know the energy of the transition state, like this one, you should minus the E, this one, E, you want to know this one. So E of the transition state minus E of the reactant, and it will give you this one. Set reactants energy to 0. Reactants energy to 0. For example, we set this as to 0. All energies must be calculated at the same level of theory. So these energies must be calculated at the same energy, same level of theory, sorry, not same energy. Okay. Now, for reactions with multiple reactants or products, like this was for the one, this was for the one, like reactants and then products. But reactions with multiple reactants or products, what you're gonna do? For that, A plus B, it gives you transition state and then converts it into C and D. There is A plus B in here. This is transition state and this is C plus D. It means there are 1, 2, 3, 4, 5 involved. What you're going to do with multiple reactants and products? You should do the summation. Energy are calculated separated for each molecule. You should calculate energy of this molecule and then this molecule, and like for example, do calculation for A and B, not for calculation A and B together. First do A and then B, like see in here, and then you should do the summation of these two, and same is for the product C and D, and then take summation of that one. If there is transition state is 1, but reactants are more, so you should do the same. Now first you should calculate the A, then B, and take summation of that, and you should minus from the transition state energy, and you can get it. Okay. Okay. So this is how relative energies can be identified. Can be calculated. 0 point vibrational energies. What is a 0 point vibrational energy? Molecules vibrate even at 0 K, what it says. But if you just want to take it at 0 K, Of course, in quantum mechanics, we say it cannot be zero all the time. Heisenberg uncertainty principle says that we cannot know simultaneously the position and velocity of the particle. If atoms stopped vibrating, they would have no velocities and well-defined position. If atoms stop vibrating, so there will be no velocities and well-defined position. Okay, why? Because Heisenberg uncertainty principle says that you can't know about the position and velocity simultaneously at the same time. So therefore, okay, let me explain. 0-point vibrational energy, this one. You can see this is harmonic. This is a complete harmonic system. And vibrational energy with n is equal to 0, like there is n is equal to 0, this one, added to the potential energy of the molecule. E total is R1, which is the coordinate, E R1 plus 0.5 h summation of I and frequency I. Okay, you see this one, V is equal to half kx square, like we talked before as well. And this is the energy, increase in energy in this direction. Okay, potential energy from energy calculation is, it gives you potential energy, and it gives you the 0-point vibration energy from normal mode calculation. Okay, it gives you what? It gives you the 0-point vibrational energy for this one. N is vibrational state. This is the vibrational state. So there is 0 vibrational state, then 1, 2, you go there. En, this is the energy. H is the Planck's constant in here, 0.5 with 0.5. And Vi is frequency with normal mode calculation. Okay, this is energy with the normal mode calculations. It means we're going to take that at 0k, and you should remember the Heisenberg uncertainty principle. If it stops, it means that there will be no velocity and well-defined position, because you can't know these two at the same time. You should remember this last equation, and this last equation which tells you about the E total R1 is equal to E R1 plus 0.5 h summation of Vi. Okay? Okay. 0-point vibrational energies. 0-point vibrational energies have small effect on relative energies. They will give you very less effect, and this one. E total is R1 is equal to E R1 plus 0.5 h. Nearly cancel out for reactants. You can see in here. And the products, there is very less. So nearly cancels out for reaction energies. Effect is often more pronounced for barrier. You can see in here, there is more. So for 0-point vibration energy is more in the barrier and less in the this one. And they have given you that there is without 0-point vibration energy and this with 0-point vibration energy. Transition states often have many weak vibrational frequency. Transition states often have many weak vibrations with low frequencies, and 0-point vibration energy correction is smaller than for reactants and products. They are often included in reaction energies and barriers if frequencies are available. For example, you can see here, this is reactant, this is product, this is reactant and product, and you can see this is the transition state. So this is the energy of the transition state. In here you can see this is 0. Okay, so that is the energy difference in these, and you can see the difference is less in reactants than products, but the difference is more in the barriers. So that was all for today's lecture. If you want to know about something, you can write in the comment below. You can also write that how can we improve, if you want us to improve the lectures and the things. and see you very soon with a new lecture of computational chemistry. Next we're going to talk about okay, today we talked about Newton-Raphson, which is very important for the most of the computational chemistry course. You know that there is harmonic and anharmonic system. For harmonic it is 1, for anharmonic you need to use the second derivative, and then the diagonal relationships are there, and the second derivative is 0 more than 0 for reactant and products, and less than 0 for the transition state. You can see the normal mode calculations. It gives you the collective vibrational motions of atoms, and then you see the frequency, which is harmonic at transition state, and it gives you frequency is equal to 1 by 2 by c is equal to k into k by mu. Have and then the normal mode calculations gives you the h is equal to pk p minus 1, and it gives you diagonal relationship, which is a force constant, and the force constant gives you the diagonal elements. It gives you k1 to k6 translation and rotation, and onward it gives you the vibrational modes. The minimum is the same point is here again, that the minimum the second derivative has more than 0 value and less than 0 for transition state. Then characterizing the stationary point, how you can just know from the structure, saddle points, and characterizing, look at the structure, the energy, which should be more than the reactants and products. You should animate it, perform IRC. Relative energy is the reaction and this one. So you can just energy of the product minus energy of the reactants, or you can take summation if there are more than one reactant and product. 0 point vibrational energy can also be taken at 0k. It follows the Heisenberg uncertainty principle. It follows E total R is equal to E R1 plus 0.5 H summation I on frequency I, which gives you the 0 point vibrational energy mode, normal mode calculations. 0 point vibrational energies, the difference is less in reactants and products, while it is very much in the barriers. That was all about today's lecture number 3. See you soon with a new lecture. Bye bye.